So we're going to spend a little bit of time looking at how to solve more systems of differential equations. We're going to look at some theory behind some differential equations. We know how to solve them. And then we will work on how we actually solve them. So first thing we're going to look at is just some theory. The derivative of x1 with respect to t is some function that's a function of t, x1, x2 through xn. The derivative of x2 with respect to t is also a different function of t, x1, x2 through xn, and so forth and so on, all the way down to the derivative of xn is a different function of t, x1, x2 through xn. This is known as a first order different system of differential equations in normal form. Normal form is because the derivative is solved for. It's first order because, of course, it's the first derivative. Another way to think of this is the derivative of y with respect to x could be some constant a11 of t. So it's a function of t, but it's not a function of x or y, any of the x's. So it's a function of t times x1 plus a different function of t times x2, all the way up to a different function of t times xn times a non-homogeneous function f of t. And same thing with x2 can be exactly the same way. And we have all of these different values of looking at. The reason we write a11 is it means it's for the first row, first equation, and the first coefficient of x1. A12 is the first equation and the second coefficient of the second variable in that equation, and so forth all the way to the end. If all the f's are 0, we call this homogeneous. So just as we've done before, same kind of ideas happen here. It's a little long to write, so we do need to have a better way to write this because we're just a little too lazy to write it that way. So x is equal to x1, x2 through xn. A2 is a11, a12 through a1n, a21 through a22 through a2n, all the way down to a and n. Is a way to kind of think of that. That those functions could also be thought of as a column matrix, which is a column of f1, f2, all the way through fn. So this is a n by 1. This is an n by 1 because it's number of rows and number of columns, and this would be an n by n. So a shortcut way to write this is the derivative of x is equal to a times x plus f. If it's homogeneous, then you wouldn't have this plus f. It would just be a prime equals a times x. And so it's just a shortcut way to write it. It just makes life easier on us because we're just too lazy to write all the rest of it out. Just to remind you about a few things with matrices. When we add matrices, it means we add the component by component. So we're going to add the 2 plus the 4. 2 plus the 4, of course, is 6. 3 plus the 3 is 9. 5 plus the -2 is 3. And 7 plus 8 is 15. So when you add matrices, you just add component by component. Notice they are the same size. You can't have a 2 by 2, this is 2 rows and 2 columns, with a 2 by 3, because then you'd have nothing to add these other numbers to. So you always need them to be the exact same size. Let's look at multiplication. How we multiply is the way we do that is we take this first row and we think of it as turn it on its side and multiply it by this first column. So one thing I want to point out before we get too far into this is that this matrix here has 2 rows and 3 columns. So it's a 2 by 3. This matrix has 3 rows and 2 columns. So it's a 3 by 2. And notice, because we are doing this, but we're turning these on the side, the number of rows and the number of columns have to be exactly the same. So these two numbers always have to equal to be able to do this. That means we're then going to add them together. So we're going to have 2 times 1 plus 5 times 2 plus 1 times -3. And then we do the same thing over here with this other one. We would have, and I need more space, obviously. So let's see. we would again do the same thing. We'd multiply the 2 times 2, which is 4. So I'm actually going to go ahead and just write what the numbers are. A little bit more space here. All right, so 2 times 1, of course, is 2. We're going to add that to 2 times 5, which is 10. We're going to add that to the 1 times -3, which is -3. Then again, we turn this 251 on its side and multiply it by the 257. So 2 times 2 is 4. 5 times 5 is 25. -6 plus 7 is -42. Is that where it belongs? Okay. Then we do the exact same thing. We take the second row and we turn it on its side and think about multiply by both of the columns. So we're going to have 3 times 1, which is of course 3. 2 times 2, which is 4. So we're going to add that to the 4. -6 times -3 is +18. Then we're going to have 3 times 2, which is 6. 2 times 5, which is 10. -6 times, whoops, how did I do that? Yeah. How did I do that? Sorry about that. We have 2 times 2 is 4, 5 times 5 is 25, and 1 times 7 is 7. Sorry, I jumped ahead. So this would be -42. And then you just have to add these together. So just do the arithmetic at this point. So the arithmetic here, you should have 2 plus 10, which is 12, minus 3, which is 9. 4 plus 25 is 29, plus 7 is 36. 3 plus 4 is 7, plus 18 is 25. 6 plus 10 is 16, minus 42 is -24. And there you have that multiplication. Technology will do this also for us, but I want you to see how to do one because we're going to be doing some of these. I'd like to first just verify that x, which is equal to 5 cosine t, 3 cosine t minus sine t, all times e to the t, is a solution to dx dt equals -2x plus 5y, dy dt equals -2x plus 4y. So we want to make sure that these are in fact equal. So the way we're going to do this is the way we verify anything. We're going to take the derivative, stick it in, and show that one side equals the other. So the first thing to do is find that derivative. Realize that this e to the t on the outside is just a scalar times this. So we just multiply each piece into it. So you're going to have e to the t times 5 cosine t. The derivative that is e to the t times 5 cosine t minus e to the t, 5 e to the t sine of t. Take the e to the t through this, you're going to have 3 e to the t cosine t minus 3 e to the t sine t minus e to the t sine t minus e to the t cosine t. And then we just plug everything in and make sure everything works for us. So a way to think of this, by the way, is that this is the matrix X prime. We're actually going to write it in that terminology. This is X prime. This is going to be -2, 5, -2, 4 times the X matrix. So we just found out our derivative was 5 e to the t cosine t minus 5 e to the t sine t. Then we had 3 e to the t cosine t. Sorry, that does not look like a cosine. Let me make that look like a cosine. And one of the things I want to point out is we have a 3 e to the t sine t and a minus e to the t sine t. So that gives me -4 e to the t sine t. We also have a 3 e to the t cosine t minus e to the t cosine t. So we actually have a 2 e to the t cosine t And then the other one was minus 4 e to the t sine t. And we want to know if that's equal to minus 2, 5, negative 2, 4 times 5 cosine t times e to the t and 3 cosine t minus sine t. And I'm actually going to leave the e to the t on the outside. That actually won't make any difference in our final answer. It made a difference in the derivatives just because of the product rule, but it won't make a difference in the multiplication here. So we'll leave it on the outside for right now. So here, I'm going to actually pull it out of this one. So we have 5 cosine t minus 5 sine t. Make sure I wrote that right because I'm starting to feel like yep, okay. And then we have 2 cosine t if I write meter, 2 cosine t minus 4 sine t all times e to the t. So multiplying this out, I get, and again, your technology will do this for you, I get minus 10 cosine t plus 15 cosine t, so 5 cosine t minus 5 sine t. And then I get minus 10 cosine t plus 12 cosine t, which is 2 cosine t. And then minus 4 sine t. All times e to the t. And notice they do, in fact, do check out. So it does work out. So it's the solution. A little bit more ideas here is we have an initial value problem. That means you could have x prime equal at times x plus f of t. And then your initial value would be x of t0 equals x0. So again, these are all matrices. Again, we can talk about when we have a unique solution. We have a unique solution as long as a of t and f of t are continuous, just like as before. We also had the initial thing where the leading coefficient couldn't be 0. We don't need that here. So just as long as this matrix a of t and this matrix f of t are continuous on an interval that contains t0, we have a unique solution. So there's really nothing new here. We do the same things we did when we had equations, when we have systems. Let x1, x2, x through xn be a set of solutions of vectors. Then x is equal to c1 times x1 plus c2 times x2, all the way to cn times xn. Again, nothing new. It's basically the same things we saw when we saw equations. Another theorem is you've got some x1, which is a bunch of different x values, x2, which is a column matrix of a bunch of x values, all the way through xn. If they are linearly independent, if and only if the Wronskian is not 0. And the Wronskian in this case is a little bit easier than we did before. The Wronskian here is just where you're going to take those column matrix and just put them into your matrix. And then you're going to find the determinant of these. You don't have to take derivatives or anything like that. As long as that's not 0, by the way, then you have a set of linearly independent vectors that form the fundamental set of solutions. We're going to go ahead and show that this x1 equals 1, negative 1 e to the t, x2 is 2, 6 e to the t plus 8, negative 8 t e to the t from our fundamental set of solutions. Normally, we need to first show it as a solution. So if we gave you the differential equation, you'd have to show, like we did with the first example, show that they both will make the differential equation of systems equal. We don't have, I didn't give you that, so I'm not going to show that in this case. All I care about here is just making sure they're linearly independent. I'm assuming that we already showed that they were solutions. So to do this, we're going to find the Wronskian. The Wronskian, again, is just a column, the matrix of these different columns put together. So this first matrix is e to the t and negative e to the t, when again you multiply that e to the t through. The second one would be 2 e to the t plus 8 t e to the t. Again, when you're adding matrices, you just add the components. So we'd have 2e to the t plus 8t e to the t. Then you'd have 6e to the t minus 8t e to the t. So all I again did was put these matrices together. This one I had to do a little bit of adding first. And now we can go ahead and find this Wronskian, which just means find the derivative, the determinant, not derivative, but the determinant. So we end up with 6e to the 2t minus 8t e to the 2t minus 2e to the 2t minus 8t e to the 2t. Combining like terms, that gives me 4e to the 2t, which since e to the anything can never be 0, that's never 0. So therefore we now know that they are linearly independent. And that means they form a fundamental set of solutions. So my solution is C1x1 plus C2x2. If you want, you can actually write this out. This would be C1, and then my x was what was my x1? My x1 was 1, -1 e to the t. So we'd have 1, -1 e to the t plus C2. My x2 was 6, 2 e to the t plus 8, -8 t e to the t. Because we want both of that to be multiplied by C2, we're going to go ahead and put it in parentheses. One more theorem is that if you happen to have a non-homogeneous, then you again have your complementary solution, which is the solution to the associated homogeneous. And then you then find the solution to the non-homogeneous. And when you add those together, you get your particular solution, and your complementary solution gives you your solution. I'd like to just verify that x of p is equal to the sine of 3t, 0 cosine 3t is a solution to x1 equals 1, 2, 3, -4, 2, 0, -6, 1, 0, x plus -1, 4, 3 sine of 3t. So just as before, you're going to go ahead and plug it in. So we're going to have to take the derivative and plug that derivative in. So let's do that first. So let's go and find out what the derivative of that x is. So again, my x is sine 3t, 0 cosine 3t. So the derivative of sine 3t is 3 cosine 3t. The derivative of 0 is 0. And the derivative of cosine 3t is minus 3 sine 3t. So we want to know if 3 cosine 3t times 0, not times 0, 0, and then 3 sine 3t, that is a column matrix. That's a 3 rows and 1 column, so 3 by 1. We want to know if that's equal to 1, 2, 3, -4, 2, 0, and -6, 1, 0 times my x. And again, my x was sine 3t, 0 cosine 3t plus -1, 4, 3. -143 times the sine of 3t. All right, so we just need to multiply this out and then add them together. So we're going to have 1 times sine 3t plus 2 times 0 plus 3 cosine 3t. So we have sine 3t plus cosine 3t in the first spot. Then -4 sine 3t plus 0, because all the rest of those are 0. 2 times 0, of course, is 0, and 0 times 0 is 0, and 0 times cosine is 0. And then we're going to have minus 6 sine 3t, again, 0 and 0. And then I'm going to add that to negative sine 3t, 4 sine 3t, and 3 sine 3t. So when we add these together, we get sine 3t minus sine 3t. We get cosine 3t in the first spot. Minus 4 sine 3t plus 4 sine 3t is 0. And minus 6 sine 3t plus 3 sine 3t is minus sine 3t. And if you look back, that was what the other side was equal to. So it does check out. So we can say, so a solution. And that's all there is to kind of doing some work with these. Again, we haven't shown you how we solve them. We're just trying to show you how we work with them.